a new data set, which it just got ready. And I hope it will be also available for download very soon. So you are the first to see this, actually, that we completed this. So our initial motivation is or was for this, doing this for the entire Arctic, was providing some support for permafrost modeling and also for climate modeling. So there has been for many years, we are working, we have ESA projects focusing on permafrost, specifically Northern Hemisphere permafrost. And part of this is using a model. It's actually University of Oslo, the Master and Westermann's group doing this, using the cryogrid model and using land surface temperature as input to produce data sets of ground temperature. And doing this also for time series going back to 1997. And that allowed us already to have a really, get an idea about how temperatures in the ground are changing for the entire Northern Hemisphere. So we have now quite a good idea where do we see the biggest increase of temperatures in the ground. So it looks quite nice if you look at it in the circumpolar view. But actually, if you go to the details and then look into the comparisons with the ground data, there are some deviations and there's some room for improvement. And there are various things that need to be improved. And one crucial item is the parameterization of the model of the soil. So so that's quite important for heat transfer, that the soil properties are right. And this eventually we hope that this helps to better tackle the modeling of active layer thickness. So that's really crucial. And what is used at the moment, what is the strategy here is to use land cover as a proxy for subground conditions. So at the moment, a global map is used from the land cover CCI. It's actually a sister project of permafrost CCI. And it's a global map, and it does not target the Arctic at all. It has not been developed for using it in the Arctic. And what was specifically of interest for this soil parameterization is where there's some organic material, like where the wetlands are, and some previous assessment of wetlands for the high latitudes. They came with this number 19% is correct, actually, regarding wetlands in the land cover CCI. And nevertheless, there were limited options that has been used until now, but we really need something better. And that's why we started to think about how could we make it better. And specifically, what we would need is something with a higher detail. Okay, the model works at 1 kilometer spatial resolution, but we need subgrid variability. And then there are many other applications. It's not only for the permafrost modeling, where higher detail, spatial detail, and also higher thematic content is actually needed. And already a preview of this, what we now produced. We call this CALU, the Circumarctic Land Cover Units. And it's a 10 meter within the extent of the, or it's north of the tree line. It's within the extent of the CAVM, the Circumarctic Vegetation Map. And we hope that this is becoming available very, very soon. Now, something else that we did already 2 years ago, which is kind of complementary, is this identification of human presence of infrastructure across the Arctic. And we used also here, Sentinel-1 and Sentinel-2, we've used it and came up with this 10-meter nominal resolution in the end. But it was, yeah, for looking at something completely different. So the CALU, that's focusing on the natural environment. And this, we call this the SACHI dataset. That's focusing on identifying specific objects. And so a completely different approach was followed. And I will present you both. So the land cover, the natural environment, how we did this, how we process the data, and how this then differs, what's the difference to what we did, what we published already 2 years ago. So I will start with the natural environment description. And yeah, so just a general comment on resolution. So Landsat has been used for many years, but there hasn't really been infrastructure data set derived from that, or there are lots of regional scale land cover maps from Landsat, so you actually can derive it, but it really makes, the resolution really makes a difference. Yeah, it's just 30 meter going to 10 meter, but for example, looking at the Thor slump, you gain so much detail, so much more information. And thinking about infrastructure objects, it's well, of course, if they are big, you also can capture that with Landsat, but the like roads and buildings at 10 meter, you are able to capture it. Of course, for many applications for permafrost, we would need much higher spatial resolution. Like for the polygonal tundra, it would be best to have a sub-meter resolution. But this is what we have. We have now this 10 meter, and this is already quite a step forward. For land cover, what's around for a long time and used a lot, it's the Circumarctic Vegetation Map, the CAVM, which is primarily based on the AVHR, and that comes at this 1 kilometer detail and resolution. And that has really nice thematic content that represents vegetation communities. It also reflects wetness gradients in vegetation physiognomy, so whether it's the shrub, tall shrub or prostrate shrub. So that's all represented in there, but it has this 1 kilometer resolution. And then there are the global maps like the land cover CCI. They also have a rather comparably coarse spatial resolution, and on top of that, a low thematic content. And unfortunately for the Arctic, a rather low accuracy. So that's the current status. So we would like to have something what has a good detail like the CAVM, and but higher spatial detail. So we did not follow exactly the CAVM, but to some extent we reflect similar properties as are in the CAVM. Now, we started to work on this already quite some time ago. So there was, before Permafrost CCI, there was a project called Globe Permafrost. And as part of this project, we developed a prototype. So at that time, we produced something. We were still working with 20 meter resolution because we were using some of the 20 meter bands from the Sentinel-2. And we did this unsupervised approach, k-means processing, and that was done for Western Siberia. So on this figure here, what is T01? So that's our initial transect where this was where the initial k-means analysis was run, and then it was labeled with expert knowledge, and some groups combined. And then we transferred this to other sites across the Arctic, where we had some people saying, okay, we would be interested to have this region covered. So we processed it at this time. And that got published already in 2019. That's available on Pangea. for download. And it's also in the APGC from ARVI in this catalog. You have the metadata and also some preview maps. So it's so you actually don't really need to download the data. You can have a look in this catalog on the maps first, what is included. So that's what we have been starting from. And as a comment also for these regions, initially we also made prototypes for vegetation height. Yeah, we didn't follow this yet for circumpolar implementation, but that's also available for these vegetation height maps for the selected regions. Now for this prototype that has already been used meanwhile, first, we in the Globe Permafrost project itself, we combined it with subsidence, actually some deviations in hot summers, and how this relates to land cover. And so these land cover types, they represent certain soil properties. So that's one of the things that became could be demonstrated by combining it with INSAR subsidence. Then it was also used for separation of frost susceptibility soils, frost susceptible soils for freeze and thaw monitoring. And in that case, actually, the method was transferred to northern Finland. So it does demonstrate, and it was validated there, and it demonstrated actually that we can also transfer it elsewhere. There has been a recent publication of linkage of reindeer herding and vegetation for the Yamal region where it was used, and it was also used for upscaling in the Yamal region of greenhouse gas for fluxes. Yes, and so we haven't had this prototype, and now we started to transfer this to the entire Arctic with the team from the company, and also including experts, regional experts for Russia, and soil experts, and Gustav Hogeus for the soils, and Xenia Ermokina for the vegetation, and some regional experts. And we now, originally we had 21 classes, now we have 23 classes, we have 10-meter resolution. We trained it over this initial transect of Western Siberia and then transferred it to the entire CIVM extent. We processed more than 3,600 Sentinel-2 granules and also created tires for Sentinel-1. And we documented we put a lot of effort into documenting these units. We call them units, as they are the output of an unsupervised approach. And we documented them with soil and vegetation data from more than 3,000 in situ records. In order to come to this 10-meter, we needed to do super resolution processing because we are using also 20-meter bands. Then what we did not cover initially was mountain regions, like steep mountain regions. And for that we needed to set up completely new the processing of the Sentinel-1. We included new classes, permanent snow and also shadow. And we revised specifically one class in the initial one, which is a disturbance class, which didn't really distinguish between different types of disturbance, but we now separated forest fires, also recent forest fires in this version. So but the thematic content largely remained the same, but we did a bit of a reassignment of how the units are called based on this the soil and vegetation data that were available to us. Now, how does what we produce, how does it compare to other data sets? The first on the left is the comparison to the prototype. It looks rather similar. Actually, it's in order to make such a comparison to other maps, we grouped them into some joint classes because there's no really any other map which has the type of classes that we have. Maybe a CIVM being rather similar, but the others are completely different, so we group them for comparison. And this there's especially the shrub tundra that we have some changes here when going from 20 meter to 10 meter. Actually, 15% of the shrub tundra were assigned to other classes, specifically wetlands, with this step to going to 10 meter. As we now have much, just by increasing the spatial detail. Yeah, in the center, that's the CCI land cover. It has largely barren for the northern area, which is unfortunately not really matching. The CIVM, you see clearly the resolution difference. And then there was also another data set produced from Sentinel-1 and Sentinel-2, which is called characterization 20, where approach was chosen to include also digital elevation model, and the digital elevation model is actually the main driver in the classification. So everything what is like in the valley is becoming wetland, what is overestimating the wetland. Yeah, so there are some issues in there. It's not perfect. So if you want to do this for the entire Arctic, you have to deal with data gaps. I thought we used data from 2016, 2022. There are still some areas where no cloud-free image was available. There's frequent cloud cover. Then we have problems with haze from fires. Then there are differences between years, wet or dry years. So when we try to capture the wetness gradients, that's it can make a difference if it's a wet or dry year. Then some cases the Sentinel-1 is lacking, like for Greenland, high Arctic sites. They have gaps in Sentinel-1 data. And then there are some quality issues with the Copernicus elevation model that we used. And we already started to replace the Copernicus elevation model with others. Specifically for Svalbard, we used a different elevation model, and we actually will have to replace it in the future also for other regions for improvement. Yeah, actually to make yearly maps of something like this for the entire Arctic is actually impossible due to specifically the frequent cloud cover. You have to combine several years. Yeah, so this is again the circumpolar version. Actually, what I've showing here is what you call the majority product. It's it's aggregated at 1 kilometer. The majority land cover in this in this grid point, and that's something that was asked for specifically from the modeling side. It's for something of interest for the climate modeling, and for it's also of interest for the permafrost modeling, in addition to the details on the subgrid variability. So this is a kind of additional product that we now made. And currently, actually, I already uploaded all the data to a repository. I hope it's can open this up soon. And we split it up into 9 regions, and in total it's 13 gigabyte. It's all at the moment in GeoTIFF. We are thinking about providing it at NetCDF, because there are some requests, especially from the climate modeling side, there's the wish to have it in NetCDF. And so this is a beta, we call it a beta version, and we are already have started some reprocessing related to other projects, looking multiple years, better translation guides for climate model, like plant functional types, things like this. Then there's another ESA project, or actually a NASA ESA joint initiative for methane in the Arctic and wetlands. So we are revisualizing the wetland representation. We're going south of the tree line and so on. So we have not, it's not really now it's done, like completed, done. So we are working on extending and improving it. So that's something what is not included, what we in there is we do not separate an artificial class. We have a barren class, but not artificial. But this is available from this data set that we produced already 2 years ago, this so-called SACHI data set. And this covers, initially that covered an area of 100 kilometers from the coast. We already updated that. It goes now a bit more further south, covers the CW-AVM extent. We added new clauses now for better distinction of roads and buildings. And that will be also published soon, this updated data set. And that can be combined if needed with this land cover data set. So we do not combine it from our side, but we supply, there are these both separate data sets which will be available. Just a few details about the 2-year the data set that we published 2 years ago for the infrastructure. So we have used combined the Sentinel-1 and Sentinel-2 to come to exploit the 10 meter. But we also combined it with Landsat trends, which can come from were processed on the permafrost discovery gateway, and we added these trends as attribute to that in order to have an idea about when did this infrastructure appear. And yeah, the approach for capturing the infrastructure, it's different from the CALU. Here we use machine learning and deep learning combination, gradient boosting machines combined with convolutional neural networks approach, plus in addition some manual quality control. So actually doing something like this does not work fully automatic. And then we combined it with this trends coming from Landsat. And yeah, just as an example, where we have a fairly new infrastructure that's on Yamal, a rail track. So that's a few years after it has been built, and we already have some vegetation recovery. So now thinking about this 10 meter, we will have a mixed pixel. That's one thing that's already something that we can use for capturing this. But it's also, if there has been some impact or something built, usually the large area around is impacted. That's just a few years before, when the rail track was a bit newer. In some places, there was actually quite some, degradation ongoing, and quite a large area was affected, and we had vegetation decline. So you see the rail track in the back. And then a few years later, vegetation had already recovered, but it still makes a difference. So it's, combining it with this 30-meter Landsat or the vegetation trends, so that we expect that gives us quite a good idea about if something is new or not. So for the next slides, I will use the specific color code. Everything what is red is new. What means what we derived from vegetation decline in Landsat. And the black is stable, and the green is vegetation recovery. But so that's coming from the 30 meter, but the object detail that's based on the 10 meter. And there's one example here, Prudhoe Bay oil field, and so the red would be everything what's new after 2000. So we see some extensions here and there, but overall the most of it is a bit older, because we have there vegetation recovery in the proximity. Some examples from Russia, some mining area near Pevek. There's uranium, tin, mercury, a lot of ongoing expansion, or especially now expansion for copper. And we see where new roads have been built, and also another example, the Red Dog mine in Alaska, where also some recent, or in the last 20 years, some expansion had happened. Yeah, so we have expansion of mining areas, but we also have a connection of places of interest for mining oil and gas. So we have new roads, and these impacted areas at the land surface from the mining itself are also included. Some other examples for in Alaska, where what we can see in many places, we see this connection to the outside, I called it, where airports have been extended or built, and then well, some extension of gold mining around Nome we can see here. Just some examples. So yeah, and that's also a bit challenging to visualize this on the circumpolar scale. So this is just now this distinction between what's new and old on the circumpolar scale. So we see where the hotspots are. Then we attach other attributes as well. This is no. Before I come to the other attributes, this is the original classes. This is the what we had: roads, buildings, and other constructions, and other impacted area. And this is what we supply also with the new version. We will actually not add other attributes to the new version, the extended version. We leave this now in the new version to whoever is using the data set. But for information, what was in the old data set, we also attached night lights. So yeah, this nice example from also the Alaskan North Slope again. We attach, and we also attach the ground temperature trends that come from the modeling here. And from this 1 kilometer resolution, we attached it to all the objects. So we can, so most regions or most objects, infrastructure objects, they experience an increase of active layer thickness, or have increased in experience increase of active layer thickness in the last more than 20 years, and also some warming occurred. But the warming, it varies from region to region. But what is kind of common to most sites is that the active layer thickness has been increasing about 1 centimeter on average per year. Yeah, so from this data set, we analyzed that, looked into it. We found that 15% of what we captured corresponds to new increased infrastructure since 2000. We found that actually OpenStreetMap doesn't really contain much detail, so we can provide, either if it's 10 meter only, we can provide much more detail than in OpenStreetMap. Now for visualization, that's actually not an idea from us, that's from the ESA, from the graphics department. They came up with this visualization of the, actually they didn't take the attributes, but they just took the spatial extent of the objects and aggregated that to these hexagons. And I think that's quite a nice representation, because you wouldn't normally, if it would be to scale, you wouldn't really see much in a map of these roads and buildings and so on. Yeah, so for the natural environment, we came up with a more regular grid. But here, I think for this, I find this actually, I think this is quite a nice way to approach it with this type of aggregation, specifically for visualization. Yeah, as a short summary comparison to the approaches that we used for the land cover units, we didn't have specific target classes. So we run an unsupervised approach in the first step. We are documenting the units based on in situ data. So we derive statistics on what's the shrub coverage, what shrubs, and so on, and also what is the soil wetness on average in certain classes based on data sets from across the entire Arctic. So that will be supplied with the data set, this information. Then, well, we use a pixel-based traditional classification. But once you come to human impact, that doesn't really work. You need something more advanced. You need some, artificial intelligence approaches. But it's not fully sufficient. You also still have to do some manual editing based on just using Sentinel-1 and Sentinel-2. And yeah, what was really important is to a really good quality of calibration data. And that's one of the reasons why we reprocessed all of it now, why we publish a new version, because we improved the calibration data and could actually improve the representation of specifically roads and buildings. Yes, so that's why it was just a very short summary of what we did 10 meter for the entire Arctic in the last years, and what we are now going to publish soon. So I hope it becomes available, and that people start using it. It will be probably for the next 2 years, the land cover under what we call a restricted access. So you don't need any login or so to download it. It's from Zenodo, but you will need to press a button for request access and to justify the use, because we want to keep some contact on with people who use it, and we would like to have some feedback about it. That feedback that something that helps us will help us to improve the data set. Right, thanks for listening. I hope you still listen.